Welcome to the 14th lecture. In the previous lecture, we discussed for the Yukawa theory, how do we write the various Green's function, the 2-point Green's function, 4-point Green's functions. We sketched how to compute it and how to take care of the relative signs whenever we have swap of fermions, because the Wick's theorem talks about all possible contractions, and to do all possible contractions, sometimes we need to swap the fermion field across the other fermion field, and that picks up a minus sign. And that eventually, for the various scattering processes, does a relative sign between the two diagrams, because if a matrix, if the Green's function or the matrix element changes sign, it is unobservable. What is observable is when the two different diagrams have different relative signs. So all that matters is to compute that relative signs, and we hinted upon that in the previous lecture. And we also talked about how to contract the field with a single particle state. Now what we do over here, we start with that and try to extract the matrix element from a endpoint Green's function. This is again has been done for you in the QFT1 course. So I'm talking about a fermion with momentum p plus the fermion with momentum k going to fermion with momentum p prime plus fermion with momentum k prime. Okay, and we already discussed how the initial and final state would look like, and it's going to two process. My initial state is p k, my final state is p prime k prime, and we found that if we just put identity between these two states, that's just the propagation of two particles into two particles without interaction. The first order, there is no contribution. The first non-zero contribution comes at the second order, and second order will have minus ig squared by 2, and then have d4x. Maybe I can shift this guy here, and d4y. Okay, and then I have psi bar, psi phi, all defined at x. Okay, and then psi bar, psi phi, all defined at y, and there's an integral over that x and y. Okay, now once we have this, we have to do all possible contractions, and we have already talked about the contracting the fields with a single particle state, the rules for that. Now what we can consider always is that this is nothing but here we have just the interaction inserted, but we can consider this is as a 4-point Green's function at second order, where all the fermion field are connected, coming in the vertices are expected to be connected to the external fields that we have provided. Okay, so first of all, the one thing that has no confusion is that phi and phi get contracted together. Okay, absolutely no confusion over here. Then we have two fermions in the initial state. So how do I create two fermions in the initial state? If I have a vacuum, I act upon them by corresponding A daggers, and now A daggers sit in psi dagger. Okay, but here what we saw in the previous class, that I can contract psi with the single particle state, initial state. Okay, and then I have a non-zero thing. So basically I have these two psi's contracted over here. Okay, so psi of y, they just say, contracts with the p, psi of x contracts with the k. That's how the initial state we define. On the left hand side, for simplicity, you take psi bar contracts with the k, and this psi bar contracts with the p prime. Okay, once we have all these contractions done, what do I have is minus ig squared by 2 d4x d4y Okay, if I have to write all this. So this is not the matrix element. This is still matrix element of the S matrix. Okay, so this is my initial state, this is my final state, and what was sitting in between was a S matrix, and then I'm doing the expansion of S matrix in order by order, and it's the second order that continues. And here we find that okay, I have, well, so first of all, this X and Y contracted together will give me a propagator, Feynman propagator for scalar, which is dx minus y. Okay, that's not an issue. Then size here contracted with p and k will keep on giving you various factors. So let me just see at y what kind of factor do I get. So at y, psi bar acts to the right, psi act to the right and psi bar acts to the left. So what I get over here, psi acting to the right will give me, let me write it here, u of p times exponential of u of p exponential of minus I p dot y it gives me. And psi bar at y contracting to the left side will give me u bar p prime, and the factor that will give me is exponential I p prime y. Okay, now let's look at what happens at the x, and that will give me u of k multiplied by exponential minus I k dot x, and u bar of k prime, and exponential factor will be I'm sorry, the first one is y, I k dot y, and here I k prime dot, okay, so these are the factors. Additionally, what we have is my df of x minus y would be d4q, let's just call it, by 2 pi 4 I exponential minus I q x minus y divided by q square minus m square, okay, where m is the mass of the scalar. When I put this particular form of f over here, so that I get minus I g whole square by 2 d4x d4y d4q by 2 pi 4. Okay, now I'll just write I divided by 2, not 2 pi, q square minus m square, and then I write all other factors, which is u bar p times u bar p prime times up. Let me put that in square bracket. This is one complex number. Then I have u bar k prime uk put as a second complex number. Okay, and then let me write all the exponential factor. Exponential minus I'll take x out. Okay, and what do I have? I have minus, with minus x comes k over here, k prime, is it? Right, with the x I have k prime. Okay, I made a mistake. Whenever I write p, it comes with y. When I write p prime, it goes to the left. Sorry, these both are y, and here both are x. My apologies for that. Okay, so I have, if I take minus x common, so I'll get k minus k prime. Okay, so k minus k prime will come from here. Take minus x common, and there's another factor of minus x coming from the definition of the propagator, scalar propagator, and that will give me plus q over there. Then I have exponential minus I y, and I'll get p minus p prime. This is the relation over here, and y comes over there with minus q over there. Okay, so this is the expressions I will have. Now I say let's integrate out d for x and d for y. Okay, so x appears only in the exponential, so that will give me delta functions. So let me just write it. Minus ig whole square by 2. Actually, I need not carry on the 2. There are two such diagrams which will add up, but let's focus on one term completely. And I have d4 q by 2 pi power 4 I by q square minus m square. Okay, and then I have this u bar p prime up u bar k prime uk, and then I have 2 pi to the power 4 delta 4, and this will come p prime minus p plus q. Okay, and another 2 pi power 4 delta 4 will have k prime minus k minus q. Okay, these are two delta function comes over here. Now I use this delta function to integrate, let's just say, second guy. First I'll cancel this and then integrate out the second guy. So what I get over there is minus ig whole square by 2, and that thing is gone, and you have u bar p prime u p square bracket u bar k prime u k I divided by k prime minus k square minus m square, because q has now this new value. I use this second guy to integrate out, and then I put that value in the first delta function, which is 2 pi power 4 delta 4 p prime minus p, that was the delta function, plus q, and q has become k prime minus k. Okay, so this is my expression of the S matrix element, which is this thing. In the S matrix element, whenever we have this, so this thing to be compared with I times the matrix element times 2 pi to the power 4 plus delta 4 sum over all momentum. Here sum over all momentum is coming out to be this, because what we have over here, if you can see, is p prime plus k prime minus of p minus of k, or in other words minus of whole thing, because what is happening over here, my p and k are incoming momenta, okay, and p prime and k prime are outgoing momenta. So if I write down the sum of all the incoming guy, then I'll have the incoming and outgoing with opposite sign. What I'll have is p plus k minus p prime minus k prime. Okay, this is equal to 0. The delta function will set it to 0. So this is the overall delta function that we will have. The rest of the things is the I times the matrix element. So this just gives me I times the matrix element is given by minus ig whole square by 2. I is still carrying out the 2, and u bar of p prime u of p u bar of k prime u of k times I divided by k prime minus k whole square minus m square. I could have written p prime minus p whole square. Okay, where I can just say that here exactly this k prime minus k is equal to q is the convention over here. So if I just use this relation over here, so it just gives me k prime minus k is equal to p minus p prime. It's just writing the same delta function in a different way. Okay, so here I could have written k prime minus k, or p prime minus p minus p prime, sorry. Okay, so this is the relation we actually have, and this is how I write the matrix element. Okay. I extracted the matrix element as such. Now point is that the contractions that I used in the previous lecture, it said that when you contract a field with a single particle thing, then the dependence on x and the momentum will be there explicitly. But when we write the matrix element, that was for the S matrix element. Okay, and then when you do some step of computation, and from the S matrix element you extract the transition amplitude, the M. Okay, so by removing this extra overall delta functions. So question is that what is the Feynman rules for writing down this M, at least in the Yukawa theory. Okay, so this is the question for which we'll just list up the things in a moment in the next page. So let me just go and here say Feynman rules. Okay, and here I'm assuming okay, this is the first theory we have involving the formulas. So nobody tells about the rule 0. I'll start with the rule 0. Draw a diagram. Why nobody talks about rule 0 is because Feynman rules is about converting a diagram into a mathematical expression. Okay, so since today for a given theory we are also going to talk about how to draw a diagram, so that's why I'm writing that draw a diagram is one of the important questions. Okay, now number 1 is about propagator, and I must say Feynman rules for matrix elements in momentum space. Anyway, matrix elements are usually defined in the momentum space, but let me just say that explicitly, because you can have Feynman rules for Green's function in real space, you can have Feynman rules for Green's function in the momentum space, you can have Feynman rules for S matrix. That's what we were doing in the previous slide. We were not doing the Feynman rules, we were computing the Feynman rules. We were computing the S matrix elements, and then from there we were extracting the matrix element, transition matrix element M. So okay, now for if I'm writing the matrix Feynman rules directly for the matrix element, there are further simplifications that we already observed in the previous slides will take place. Okay, so first of all, when I talk about propagator, so it is phi of x, phi of y. Whenever you see this propagate with this contraction, this is df x minus y is defined to be d4 p by 2 pi power 4 I exponential minus I p x minus y divided by p square minus m square, where m is the mass of the scalar, and it is denoted by a broken line, okay, with momentum p flowing from one side to other side. Okay, so whenever you have x and y thing, only xy dependence remains this. Okay, my apology, I'm doing in the momentum space. Okay, so I don't need all this garbage. Okay, so whenever you see this, you just denote it by broken line thing with momentum p, and expression wise it is I divided by p square minus m square. Apologies for that little diversion. Okay, if this is the p is the momentum, this is how you write it. Now when you have fermion psi of x, psi bar of y, this contraction, you draw it by solid line with an arrow, and the arrow is the direction of momentum, And momentum, the convention is momentum is flowing in the same direction as arrow, and then you write it I times P slash plus mf. Mf is the mass of fermion. P square minus mf square plus I epsilon. I'm sorry, here I forgot the I epsilon, which is the Feynman propagator. Okay, so this is for each propagator, this is what you write. Then comes the vortex. In this particular theory, we have the vortex defined as such: a fermion coming in, a fermion going out, and here a scalar is interacting. And this is nothing but minus I times G, because between psi and psi bar sits an identity matrix. So here you can just say that identity matrix is sitting, but we don't really need to explicitly write down the identity matrix. So these are the three pieces of right. Now there's most important thing comes here, the external leg. Okay. So with regard to external leg, if I have a phi contracting with a momentum q, single particle state in the initial or final state, okay, so this is diagrammatically, it is that somewhere it is, and it is the initial state. So this is the, let me draw it differently. Okay, so here is the initial state scalar, which is somewhere coupled to the fermion leg. Okay, so I'm talking about this. How do I write down this guy? This is connected to the vacuum. Okay, is contacting with the vacuum, and this is denoted by just one. Okay, this is the initial state. Okay, so I start with a guy, and it is connected somewhere in the fermions. Now for the final state, if there's a q final state phi, this is the contraction. This is something like you have some fermions, and then this is the final state fermion going. Okay, so here q is incoming into the diagram, here is q is outgoing of the diagram. Okay, and this is also equal to 1. For scalars, this is exactly 1. Okay, now for incoming fermions. Okay, incoming fermions is like psi acting on single particle state. Okay, this is a fermion state. I write PS for the anti-fermion state also, so let me write it. Fermion. So this is like a fermion line coming in, and P is in the same direction. Okay, and here is the rest of the diagram. Okay, so this is the rest of the diagram. Here this is the rest of the diagram. This is the rest of the diagram. And so initial state fermion is going to be US. Okay, and for the final state, P and S, there we will have psi bar contracting with this. Okay, so this is something like some diagram. Okay, and here fermion is going out, and P is in the same direction. Okay, as the fermion thing. So here I'll have U bar S of P. Okay, no exponential factors that we were talking about. Next I have anti-fermion. So anti-fermion in this initial state is psi bar acting on P and S. Okay, this is anti-fermion state. Okay, and this is again fermion line coming in to the diagram, but here incoming guy has fermion line going in the opposite direction while the momentum flows in this direction. Okay, and this will be VS bar of P. Now for the final state, P S, the momentum and all this thing, psi contracting with this is this is the diagram, rest of the diagram, and here is the fermion. Momentum is flowing outside, fermion line is flowing inside, okay, and this is equal to Vs of, so final state fermion is U bar, final state anti-fermion is V, initial state fermion is U, and initial state anti-fermion is V bar. So this is how we'll write down the external legs, the contributions from the external legs. Okay, and don't forget here that maybe I should explicitly write that this particular model has identity, and if we had a pseudo scalar coupling of the scalar with the fermion, this identity would have been gamma phi. Okay, that's my term in the Lagrangian. So just to remind that this is coming from the term that G times psi bar times identity psi phi. Okay? It is coming from that particular term. In the Lagrangian, if I must say, it had a minus sign, so you just multiply by I, and these are the rules for I times M. Okay, maybe I write it. This is the rules for I times M. We are trying to write I times M. So draw a diagram, that's rule 0, and then for propagator you do this. So what it says here is only one vortex in Yukawa theory, you do this. For external leg, these are the bunch of rules for the how to do it with the scalar and how to do it with the fermions. So scalars you already know from the previous course. Fermion is something new in this particular course. Then rule number 4, rule number 4 is impose energy momentum conservation at each vertex. This is your rule number 4 for writing the matrix element. If you do this, then what happens that whatever momentum you have written, you can write that in terms of the initial and the final state momentum. Not when you have a loop in the diagram. Then what happens that the number of free momenta to be evaluated is more than the number of initial number of the delta functions. Okay, so some of the momentum remains indeterminate, so that's called the loop momenta, and the Feynman rule says integrate over each undetermined undetermined loop momentum. Okay, momenta I should say, because there can be many. Important thing about 6, okay, is divide by the symmetry factor and compute the fermionic sign. Okay, so fermionic sign of the diagram is need to be computed. That after all the switchings and all this thing, that we put our propagators in the right order, whatever overall sign it is. Okay, so compute the fermionic sign. Yeah, so perhaps I should say overall sign. Compute the overall fermionic sign. This is your rule number 6, and you're done. Okay, what you need to look after is that important thing to note. Okay, that fermionic loop always means a factor of -1, no matter what is the size of the loop. In the loop, you always have even whatever number of propagators, you always have even number of fields because each propagator coming with the 2 fields. Okay, and when you sequence them together, there's one guy which has to taken over all across to the other side. All across to the other side means there only odd numbers are left, so it is always gives you a minus sign. So fermionic loop will always get to the minus sign. That's one thing. Okay. Second things, we need only the relative sign between the diagrams. Okay, overall sign actually doesn't really care, because if there's only one diagram and if it happened to be a minus or if it was plus, how does it matter? We are going to take matrix element square. Now if there are more than one diagram, then one diagram having plus and other having minus matters. Okay, because the interference will be different and that can be measured. But overall sign of the entire sequence, if it's the same, then the relative sign is basically positive, and so it basically doesn't matter. So what we care for is the relative sign between the diagram. These are the two important things to note over here. Now before jumping ahead, I'll focus your attention on the rule 0, which says the draw diagram. Now what do I mean by draw diagram? I have a Yukawa theory. Okay, and usually what people ask is a question is that draw me endpoint Green's function at one loop. Why people talk about this particular thing is the number of external legs describes what kind of process or what kind of phenomena I'm looking at, and number of loops basically also tells me, apart from the fact that how much higher order in the interaction it is, it also tells me the computational difficulties. So usually I would like to start with a 0 loop because there are no momentum integration to perform. You remember rule 5 was to integrate over all the undetermined loop momenta. Now if there are no loop momenta to be determined, as it was the case in the previous example that we were looking over here, there is no momenta left. All the momenta are explicitly known, right? The only thing unknown was in the between, and the delta function gave me that. Okay, but when we have loop, this was a tree diagram. I will describe those diagrams in a moment. So when we have some undetermined loop momenta, then evaluating those matrix element becomes technically challenging. So whenever one asks to write down something, they don't say that give me third order in the Hamiltonian, because as we will see in a moment, that order in the Hamiltonian is not the order of complexity, but the number of loops, which means how many integrals you have to perform, defines the order of the complexity. Okay, so we will discuss that in the language of graph theory. So till now we have been talking about fermions and scalars and blah, but we are going to completely unhinge ourselves from all that notations and talk about the graph theory, that how to draw a diagram. Okay, so let's begin. Graph theory. Okay, so what is a graph? G is defined as a doublet involving two sets, where V is set of all vertices and E is set of all edges. This is nothing but propagators for us. Vertices are the interaction vertices, but I can have the initial and final state also described as a one-point vertices. Okay, so that's the so to say starting point for any graph. And there are certain things that we need to define, which is degree of a vertex is equal to number of legs at the vertex. Okay, so let's have a little discussion. This is a vertex, okay, and that's it. That's the only leg. So this is d is equal to 1, degree is 1. Here is a vertex which has 2 legs, d is equal to 2, and we'll see that this is not very useful for this is not required in QFT. I'll describe it. It doesn't even appear. There is a logic behind it. Here is a d equal to 3. Here is d equal to 4. These are different kind of vortices you can. Okay. Now I have to write certain things that involves some numbers and all these things. So first of all, none of these are diagrams because I'm only drawing the vertex from which the legs are starting, but where they are going. In a diagram, each leg, each edge is connecting two vertices. Okay, and so edge is connection between two vertices. Here I have not drawn the second vertex. It says that it goes somewhere and usually to some vertex. Okay, so this is not the graph. Graph would be something like this is a graph. Okay, this is my propagator, 2-point Green's function. This is a graph. Then I can have what we have talked about. This is a graph. This is a graph. Okay, and so on. We also have talked about graph like this. Okay, this is the kind of graphs we talked about till now in Yukawa theory, where each line is a propagator, was a propagator in those theories, either fermionic or bosonic, but here we are unhinging ourselves from those descriptions. So these are the examples of graphs. Okay, so these are the graphs on the left hand side. On the right hand side, I'm just saying that what is a degree. So here you can see in the first guy, let me just select it. Here I have 2 vertices, each one having degree 1. Here, sorry, in the next one I have 3 vertices externals which have degree 1, and the central guy has degree 3. In the next one I have 2 vertices with degree 3 and 4 vertices with degree 1. In the lower left I have 2 vertices with degree 1 and 2 vertices with degree 3, and here again I have 2 vertices with degree 1 and 2 vertices with degree 3. Okay, so these are just to say that what kind of diagrams we have. Now comes an important result about any diagram, any graph, is called Handshake Lemma. Okay, so what does it say? It says that look at all the vertices, all the V, element of capital V, okay, and look at the degree of the V. Okay, so dV is the degree of V, V vertex, where V is an element of set V. Okay, or maybe I just overusing the letter V over here, so let me write it I. Right. Running index is I. So I is an element of I is one of the vertex, and di is the degree of that vertex. So if I sum all the degree of the vertices, what I am doing, okay, you can check that what I'm doing for each vertex I'm sitting and says, okay, let me count how many legs are connected to that vertex. Okay, and I'm doing it for each vertex and summing up all over the graph. So what is it equal to? So if you see the definition of edge, it's connecting two vertices. So each edge is connecting two vertex. That means each edge is getting counted twice, once on the one side edge and second time in the second side edge. So if I sum up degrees of all the vertices, what I'm expected to get is 2 times the number of edges in the graph. So what this notation you might know, that if E is a set, mod E is the number of elements in that set. Okay. So this is the handshake lemma. The sum of degrees of all the vertices is equal to twice the number of edges we have in the graph. You can check it over here. Here degree 1 and degree 1 in the first diagram. Okay. So 1 plus 1 is 2, and that is 2 times the one edge that I have here. Now look at the next diagram. I have degree 1, 1 and 1 coming 3 times. So that is 3, and 3 coming 1 time. So the 3 plus 3 is 6 is the total number of it is somehow all di, but here we have 3 edges. So that is 2 times 3 is 6. Come to the last diagram on the top row. I have 4 vertices with degree 1, that's 4, and I have 2 vertices with degree 3, so that is 6. So 4 plus 6 is I should keep on writing, 4 plus 6 is equal to 10. Okay, and that is 2 times 5, because there are 5 edges. Likewise here, if you see, here I have 1 plus 1, so here 2 plus 6 is equal to 8, which is 2 times 4. Okay, I have 1, 2, 3, 4 edges, like same numbers in the next last diagram also. The handshake lemma is very intuitive and very simple. This is my first result that I'm going to talk about. Next one is a bit more involved. Okay, so there, in fact, I don't even know what to call it, so I'll just say Euler formula. If you look by the name Euler formula, I am not sure you will get this. Okay, so first of all, before I go to the Euler's formula, I define something, and again, when I say Euler's formula, it is what I am calling it. So the formula's actual name I don't know. So tree graph. What is the meaning of tree graph? A graph with no loops. Loops is the wrong word. In graph theory, they use loop to mean something different. No closed cycles. Okay, closed path, one should say. Just say no cycles. So all the diagrams that we draw over here on the top row are the trees. Okay, because there is nothing that has closed loop here. In the bottom row, I draw 2 diagrams and they have closed paths, right? I can start from a given vertex, go along the graph, come back onto the same node. So that is a closed path. So whenever you have closed path, that is not a tree. So tree is something where there is no closed path. Okay, so that's important thing to start with. So again, what we can say over there, a different kind of formula, different kind of notation that we see. Let's look at the first guy. What do I have? Number of edges is 2, and number of vertex is number of edges is 1, and number of vertex is 2. Okay, number of edges is 1, number of vertex is 2. So Euler formula step 1 that I will write for tree diagram for connected tree. Connected tree means there is only one tree. Okay, not 2 trees sitting next to each other will be called disconnected tree, because it satisfies there are no cycles. So the combined tree is also a combined graph, is also a tree graph. But since there are 2 different components, this formula will not hold. So for a connected tree, which means a single component, single connected component, is for this I can write the number of vertex minus number of edges is equal to 1. You can check it. Let's try. Sorry. Here 2 vertex minus 1 edge. Okay, 2 minus 1 is 1. Here 4 vertex, 3 edges. 4 minus 3 is 1. Here 6 vertex, 5 edges. 6 minus 5 is 1, and so on. No, it is not valid for loops. Okay, you can see here we have 1, 2, 3, 4 edges, and 1, 2, 3, 4. So 4 vertex and 4 edges. So that's 0. Here also 1, 2, 3, 4, 4 vertex and 4 edges. It's 0. It's not valid for this guy. So I'm saying for the tree graph, I have v minus e equal to 1. Now let's consider these two tree graphs together. Okay, so here I can just say this guy and this guy. If I consider them separately, then it's fine. But if I consider them together, what happens? Number of vertices is 1, 2, 3, 4, 5, 6. So 6 is the number of vertex minus number of edges 1, 2, 3, 4. Okay, so that becomes equal to 2. But what is this 2? What I had is v minus e is 1 for each component. Okay, so when you have multiple components, then what happens? Multiple component tree. Okay, then v minus the edge is number of components. Okay, so that's how I'm developing my formula. Okay, and that's not it. Okay, so let's keep it. That's one way I can extend. Now start from the v minus e equal to 1. Okay, and let's look at this particular diagram. This particular graph. Okay, so if here I add, let's say here v minus e is equal to 1 is satisfied. Now if I have to add another edge, so I want to increase e. Okay, if I want to increase e, what I do, I add an edge, but I have to add a vertex like this. Okay, I have no option. But what if I don't want to increase the number of external vertices? Okay, I don't want to. I start with some edge. So even if I start from here, okay, here it is. I added one edge, but I added one vertex also. So v is increased by 1, e is increased by 1, difference still remains 1. Okay, so I want to do something like this. No increase in vertex, but increase in number of edges. So more edges than what this formula supports. Then immediately I realize that I no longer have a tree. Now I have one cycle, one loop. Okay, so here what happens, that v minus e, which is equal to the number of components, if you increase the number of edges, you increase the number of loops. So it comes with a negative sign. Okay, so you just subtract the number of loops. So this is the formula that is my final formula, which I am gonna call Euler's formula, but I don't think it's a correct name for it. Okay, so this is the guy. V, number of vertices minus number of edges, is equal to C, which is number of components, minus L, number of loops. And the previous formula, which is called Handshake Lemma, here it talks about twice the number of edges is related to the sum of all the degrees. Okay, I'm going to combine this to formula and eliminate the number of edges from my expression. Okay, I can write this guy, this particular thing, I can write V minus C plus L is equal to E. I can start by writing like this and then multiply on both sides by 2, because the previous formula is about 2 times the number of edges. Okay, so before I do this, let me just write all the things that I need in this formula. Okay, so first of all, by combining this, I immediately get I element of V di, that is 2 times the edge, is equal to 2 times the number of v, because edge is related to this, 2 times c plus 2 times l. So this is my working formula. Okay, now say in a given graph, let there be n1 1 point vertex and 2 point vertex, and so on. Okay, then this just gives me that sum over di I element of v is nothing but n1 plus twice n2 plus thrice n3 plus so on. Okay, plus d and d and so on. Okay, at the same time I know that number of vertices is nothing but n1 plus n2 plus n3 plus so on, plus nd plus whatever number of other vertices I have. Okay, so I can put these two formulae over here, so it gives me this formula that I have written, gives me n1 plus twice n2 plus thrice n3 plus, just let me write one more thing, 4 times n4 plus dot 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 plus d times nd plus blah 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 is equal to 2 times n1 plus 2 times n2 plus 2 times n3 plus 2 times n4 plus blah 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 plus 2 times nd minus 2c plus 2l. So this n2 cancels on both sides. That's what I wanted to say. N2 would not appear in the expression, and I want to put n1 and all this c and l on one side and put everything to the other side. So the expression that I will get is n1 minus 2c plus twice l is equal to n3 plus twice n4 plus blah 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 plus d minus 2 and d plus blah blah blah. Okay, this is the expression. Why I wrote it like this? Because people usually ask a question based on complexity, as we were talking about, that give me endpoint Green's function and we at this loop, because the endpoint Green's function tells which kind of processes we are interested in, and number of loop tell me what is the computational complexity for that, and c usually is equal to 1 because we want a connected diagram. Okay, we don't care for the disconnected diagram, but this formula is general and it does apply for disconnected diagrams as well. So when people say that draw a diagram, that what they meant is a single component diagram, okay, not a disconnected diagram. Okay, and you can see n2 doesn't appear, n2 nicely cancels out because n2 is a 2-point diagram. So if I have a diagram, okay, with so when I say this, so I meant some part of the diagram is here, then there is a propagator, and some other part of the diagram is here. So I don't know what these two bunches are, but this can be written as, okay, this is your vertex, you insert 2-point vertex, this is the same. Okay, so I inserted this 2-point vertex over here. It did not change the diagram at all because I can stretch the any propagator by inserting any number of 2-point functions, and actually it doesn't change anything about the diagram, that it doesn't change the number of loops, okay, and all that thing. And usually what happens whenever you have 2-point Green's function, that usually means that your fields are appearing twice in that particular term in the Lagrangian, and if some fields is appearing twice, it's just a propagator, it's related to a propagator. Okay, and usually these things can be solved exactly by some kind of diagonalization or redefining of the fields. So that thing simply says that you don't need a separate Feynman diagram or Feynman rules for that. You don't have 2-point vertices in your diagram. You set up your theory so that you don't need 2-point vertices, although sometimes one needs it, and one has to put an infinite possibility of insertions of this guy and then sum them up. And there are certain models where this is important. These are models when the different fields mix with each other. So all the mixing terms are just 2-point functions. And if you want to do your computation in a basis where the diagonalization hasn't happened, then you have no option but to use the 2-point functions. Okay, but that's just another detail. So here we will talk about the situation where the interaction means you have at least n3, n4, and so on. Okay, 4-point functions and all this. So this is n4. Okay. So usually, as I said, the questions would be based on a number of number of external legs and number of loops you have. So for Yukawa theory, here I can just say for theory, n3 is a variable. Okay, n3 is a definite variable, and n4 etc is equal to 0. So n4, n5, n6 is 0 because theory doesn't support 4-point, 5-point, 6-point vertices at the tree level in the Lagrangian. Lagrangian does not have 4-point vertex, 5-point vertex, and all that. We just saw there's only one 3-point vertex, 2 fermions and a scalar. Okay, this is the only thing it has. So we consider only n3 to be non-zero. Okay, so now I can ask this question: how about, so, and n1 is a number of external legs, and c will always take equal to 1. So take c is equal to 1. So this gives me n1, which is the number of external legs, okay, plus 2l minus 2 is equal to n3. This is my formula where n3 is a number of vertices. And also, since the vertex will come, number of vertices is same as the number of the order in the Hamiltonian. Okay, to have one vertex, I need one insertion of Hamiltonian. To have two vertex, I have two insertions of Hamiltonian, and so to the second order in Hamiltonian. Okay, but again, as we see that is not the defines the computational complexity. Is the number of loops that define. So if I have n2 is equal to 1, okay, and L is equal to 0. N2, so N1 and L I found, then that gives me the value of N3. So that just says N3 equal to 0. N1 is 1, so that's, I'm sorry, N1 cannot be 1, N1 is 2. I wrote completely weird stuff. N1 is equal to 2, not N2 equal to 1. N2 doesn't appear. The number of external leg is 2, number of loop is 0, the 2, and number of loop is 0. So 2 minus 2, here the formula itself contains minus 2. So this 2 cancels out, L is 0 anyways. So you get N3 equal to 0. And what kind of diagram we have? This is the diagram we have. Okay. Then let's just say N1 is equal to 2, L is equal to 1. That gives me N3. Okay. If L is equal to 1, then the 2 times L that survives, and N3 is equal to 2. The diagrams that you see are of this kind. One diagram of this kind, one diagram of this kind. Okay, we saw these 2 diagrams. Okay, that belongs to N2 equal to 2. Now here we see, when I actually compute these diagrams, then the integrals will have to be computed. Okay, and right, and here we have N4. Let's try N4. Okay, we can also try n3, nothing wrong with that. We have not talked about that, so let's just try n1 is equal to 3 and L is equal to 0. So 3-point Green's function, n3 is equal to 3, L equal to 0. So 3 minus 2 equal to 1, so that gives me n3 is equal to 1, and the diagram would be, so what is this diagram? And this is like two fermions going into a scalar, or a scalar decaying into two fermions. So this is a kind of decay process kind of stuff. No scattering process, but decay process. Now if I say n4 is equal to, or let me, before going to n4, still continue with n3. Bad notation. N1 is equal to 3 and L is equal to 1. That gives me n3 is equal to 3. Okay, and example for that diagram would be, this is a 1 point, this is a 1 point, this is a 1 point, this is one of the 3 points, and other 3 points are this kind of loop diagram. Okay, this is 1. I can also write this. Okay, so here these 1, 2 and 3 are the n3 3-point vortices. Okay, now let's look at 4-point Green's function. N1 is equal to 4 and L is equal to 0. But here, before we go ahead, let's just go here. So for single propagator, there is no vortex, means no, this is just the basic level. Okay, for the free Hamiltonian and the propagator. Okay, beyond that, it is second order in the Hamiltonian, but it has loop 1, the 2-point Green's function, so it requires computational complexity. When you go to 3-point function, is first order in the Hamiltonian. We noticed that both 2-point and 4-point Green's function that we're talking about in Yukawa 3 did not receive any contribution from the first order, but the 3-point Green's function will. Okay, that is first order in the Hamiltonian, and computational complexity is 0 because there is no loop. Okay, and when you have third order in the Hamiltonian, will have one loop, so its computational complexity is on par with the any one loop computation. But when you say n1 equal to 4, L equal to 0, that gives me n3 is equal to 2. Diagram is this. These are 4 1-point external legs, and here the 2 n3s. Is a scattering process. Okay, it could be 2 scalar going to 2 scalars. Can it be? No. It can be 2 fermions going to 2 fermions. It can be 2 fermions going to 2 scalars, or 2 scalars going to 2 fermions, like that. So here the computational complexity, which is decided by the number of loops, is practically 0, but it is second order in the Hamiltonian. Okay, so we can see that terms which is second order in the Hamiltonian, but computational complexity is 0 if the number of legs is higher. Okay, and so on. Here let me just last one write, n4 equal to 4, L equal to 1. That gives me n3 equal to 4. That previous formula that we have, this formula, n3 is equal to this, n3 will be 4, and one of the possible thing is just this diagram. Okay, I'll write another diagram. Okay, these are all one loop diagrams, and depending upon the exact topology, they have different meaning and all these things, which will come to when we talk about ring normalization. Here is just drawing a diagram. This is all about drawing a diagram. How do we draw this? Okay, and we use graph theory for that. We use this master formula, because usually people ask, this is the endpoint Green's function connected, that means c equal to 1, at these many loops is what you have to draw, and then convert that diagram using the Feynman rules into an expression, and then compute that expression. By computing that expression, the L defines the computational complexity. Okay, so if we want only the simpler diagrams, we just set L equal to 1, L equal to 0, that is to say, and then this formula simply becomes C is 1 and L is 0, then N1 decides some of all other stuff. Okay, if you want to calculate only the tree level diagrams. So how many vertex of what kind you would need? Here, since this is a simpler example, we don't really have much of a complexity. Let's have another example. Okay, their model is Dirac plus sign codon. So this is a fermion, this is scalar, and then I have minus g psi bar psi phi. This is my Yukawa term, minus lambda by 4 factorial phi to the power 4. Okay, now one can write the Feynman rules for this. You know how to write Feynman rules for this term. We already saw how to write the Feynman rules for this Yukawa term. So one can write the Feynman rules for all of this, not an issue. Okay, important thing to note over here that N3, which is a 3-point vertex from here, and N4 are variables, and N5 etc is equal to 0. Then my expression becomes for this particular 3 N1 minus 2c plus 2l, right? That was the expression. I'm forgetting. Yeah, minus 2c plus 2l is equal to N3 plus 2 and 4. Okay, with a constraint that N1 and 2 and 3 are greater than or equal to 0 and integers. Okay, we have to draw this diagram. I did not draw, did not ask a couple of things, which is the N1 equal to 0. One could have asked. So let me go to the previous page and ask N1 is equal to 0. Okay, when I put N1 equal to 0, what options do I have in this section? N1 is equal to 0. If I put L equal to 0, then N becomes a negative number. Not possible. So I cannot put L equal to 0. Okay, so I have to put L equal to 1 at least. Okay, so when I have N equal to 0, then I put L is equal to 1. Okay, and that gives me N3 equal to 0. So what is this diagram? It is just a circle. Okay, this is just a circle. Now then I ask, how about L is equal to 2? Okay, if there are 2 loops, N1 equal to 0, 2 loops. Now what happens? 4 minus 2, that is N3 equal to 2, it will give me. Okay, that gives N3 equal to 2, and we have seen this diagram. Here is the vertex, here is the vertex. We have a diagram like this. We have seen this diagram. Okay, so these are all called bubble diagrams. Okay, these are and they will appear in the denominator of that expression that we had, because there is no external x over there. So we have seen this kind of stuff. Okay, so this is possible, but when we come to this particular theory here, then ask, what if, okay, N1 is equal to 2, L is equal to 1, and of course C is equal to 1. What it gives me? Okay, it gives me N3 plus 2 and 4 is equal to what it gives me? L is 1, so that's 2. C is 1. Okay, that's 2, so that cancels out, and that is N1. N1 is 2. So I have this expression. Okay, so this, there is a two way to solve it. So n1 is equal to 2, sorry, and apologies, so there are two solutions. So n3 and 4 is equal to 2, 0 will satisfy it, and 0, 1 will satisfy it. So in 2, 0 case, we know this is what we saw earlier. Okay, these are two one loop diagrams which takes 2 and 3 vertex, 3-point vertex. How about this one? This is this, 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 this. This is 1 4-point vertex. Still one loop, 2 point. Okay, so there are different ways. So this tells that this, in this category I have this diagram, in this category I have this diagram. Okay, that's very important to categorize it properly, because we will need all this information when we are doing renormalization. We need to, and we need to further subcategories we will also have to work with. Okay, now here if I just say so already you can see between two variables I have this option. So of course when you try to solve this equation, there are quite a few solutions you may be able to find, but I don't want all possible solution in n3 and 4 plane. n3 and 4 plane, I only want the solution in the first quadrant, and usually these guys will have plus between them with different coefficients, so it will be like that. Negative slope equations will be, so there will be finite number of solutions. In this particular case, n3 equal to 2, n4 equal to 0, and n4 equal to 1 and n3 equal to 0. These were two solutions. There can be some more kind of solution. An important thing to note that both n3 and n4 has to be integers, 0 or positive. Okay, so there are going to be finite number of solutions to this, and then corresponding to those there will be finite number of diagrams, finite category of diagrams you can form, actually finite numbers. Okay, so this is how we'll do our graph theory. We can ask for different kind of diagrams here from here on, but let me stop over here for the purposes of graph theory. We'll use this information whenever we do expansions of these guys.